Viscosity. First of all, you must know viscosity is not a physical quantity, it is just a property like friction, like elasticity. It's a physical property. What is viscosity? A tendency to oppose the relative motion between the layers. Layers of what? It might be the layer of liquid, it might be layer of fluid. That means it is a common property for both, that is liquid and gases as well. You could say this is analogous viscosity. Viscosity is analogous to friction. That's why it is also sometimes given the name fluid friction. You see, because of this viscosity, the force arising would be called viscous force. Likewise, in friction, we use the term frictional force. Frictional itself is a property, whereas frictional force is a physical quantity. Similarly, here, viscous force that will arise because of viscosity will be known as viscous force. This force will depend on the area of contact. That means the two layers are in contact, their contact area will be considered here. You know, velocity gradient, you must be aware of this term gradient. Gradient could be used with pressure, with potential energy, with temperature, with potential itself. Gradient simply means the rate of change with distance. When you say velocity gradient, it means the rate of change in velocity with distance. You see, when river flows, the velocity at the bottom is quite less. As you go on higher, the velocity goes on increasing, and ultimately on the surface, the velocity is maximum. You see, if between the two layers, the distance is dx and the velocity is v plus dv here, this is v. You see, the velocity is in ascending order. Quite at the bottom, the velocity is almost zero. That's why it is said when you drop some coin, that will go in the bottom and that will remain stationary. That will remain where it is today. Even years after, also you'll find the coin at the same very place, because the water at the bottom is not in flow. You see, the change in velocity between the two layers is dv. dv upon dx, this is known as velocity gradient. If you combine the two results, you find a delta v dx, and if you put one constant, this would be the equation. This equation is also known as Newton's equation for viscosity, although this name is not very popular, but even then you must know this is known as Newton's equation for viscosity. Sometimes minus sign is also used over here just to show that the force that is applicable here always opposes the motion. It's a kind of negative force from that point of view. That's why it's used as negative sign. Coefficient of viscosity, you could find the dimension, you'll find this in L minus 1, T minus 1. This is coefficient of viscosity. Sometimes you see it is compared with modulus of rigidity in elasticity. There you call it modulus of rigidity, and here we call it coefficient of viscosity. Its unit has been shown over here. This is Pascal second in SI. It's known as Pascal second. In CGS system, this is known as pies. Actually, this unit is based on the name Paisley, scientist Paisley. In short form, in CGS, we use the term pies. This is very uncommon. Most peculiar or popular unit is this one, Pascal second. Now, Stokes' law. You see, one list has been given here in tabular form for different kind of liquids. The coefficient of viscosity has been given. These are the powers, 10 to the power minus 3, minus 5, and so on. These are the values for water, air, glycerin, and mercury. The coefficient of viscosity has been given. Now we will study what is Stokes' law. Stokes' law deals with a body mostly solid, but that's not exclusive. It is applicable for liquids also. It is mostly, we are conversant with this law for solids in general. When a ball or a body falls inside the liquid or even moves means it could move horizontal as well. When the body moves inside the liquid, a viscous force will always oppose. That is a kind of drag force, it will oppose the motion. That opposing force is given by 6 pi eta r v. One question arises, and that's a very uncommon, very remote question, that many times students ask, sir, is it applicable for the circular spherical bodies only? No, not at all. Here we are using radius because we are applying this law for sphere, spherical ball, spherical object. But suppose in place of a sphere there is some other zigzag object, irregular shape, then also this law is applicable, and there we use another term here that's known as characteristic length. So do remember, this is not confined to spherical objects only. For a sphere you could say this is 6 pi eta rv, r is the radius of the sphere. Now when a body is falling inside the liquid, this force that is acting upward will be 6 pi eta rv. This is the viscous force. The weight of the body will act downward, v rho g, weight of the body. Because of gravity, weight always acts downward. Here also the weight will be acting downward. When the body gets immersed inside the liquid, a thrust will act upward, and that's given by V sigma G. Body is subjected to 3 kind of forces. Ultimately, you see, a situation will arise when the outcome of these 3 forces becomes 0. That becomes a very critical situation when a body falling down is subjected to no force. Obviously, its velocity is going to be constant, because only force is responsible for changing the velocity. When there will be no force, the velocity will be constant. That particular velocity will be known as terminal velocity. So in that case, you equate all the upward forces with the downward forces, and that becomes V rho g, that is equal to V sigma g plus 6 pi eta r v. V is volume. You could place 4 by 3 pi r cube in place of volume, and if you put the values and solve, finally you are going to get the velocity given by 2 by 9 r square rho minus sigma g upon eta. This value of velocity will be obtained only when you equate upward forces with the downward force. That means net force you are considering equal to 0. This velocity becomes constant, so this would be known as terminal velocity. One very important aspect of this equation is that terminal velocity depends on the square of the radius. If you plot a graph between terminal velocity and radius, it's going to be parabolic. One more thing, if you are interested in plotting the graph for the body falling inside the liquid, you see the velocity will be exhibited this way. Velocity of the falling object will gradually increase, and ultimately when net force becomes 0, it's going to be constant. That is terminal velocity. If you are interested in plotting the graph between displacement and time, it's going to be this way, like this. Why? Because when the velocity becomes constant, ST graph would be linear, having no variability in shape, and till it is variable, it means there is acceleration. When the force will become 0, only then the acceleration will become 0. Remember, the acceleration doesn't fall suddenly. Acceleration decreases gradually and ultimately becomes zero. Then only the terminal velocity is obtained. So, these are the popular mechanics graph: velocity, displacement, acceleration, bit time for the body falling inside the viscous fluid when Stokes' law is applied.